Diskusie pod lampou existujú iba vďaka vašej podpore. Ak považujete program pod lampou za zmysluplný, pomôže nám už 1 euro za diskusiu. Vopred vám veľmi ďakujeme.
Good afternoon. It's a great honor and pleasure to welcome here Professor Michelom Mayorom, astrophysicist from Switzerland, from University of Geneva, and Nobel Prize winner, and the chairman of the Committee for Asset Science Award this year. That's why we have him here. The main discovery Michel made is a discovery of planets outside of our solar system. And when people hear about discovery of this kind of planets, I think they almost everybody saw it in blockbuster movies, planet of this type and that type. So I think that when I will show you the main picture from the article from 1995 in magazine Nature, you will be disappointed, because there is no nice planet visible at that picture. It's quite a boring picture. It will be for you. But the good point is that if picture like this is worth Nobel Prize, then perhaps also you can win it sometime. And now, Michel, I would like to ask you to tell us where here in this picture is the planet, or how is it present in this picture?
Yes, I really love to see this diagram. It was so important for me, this boring big picture. So I believe we have to explain what is behind. Planets only reflect a small amount of light coming from the star. Let's imagine you are looking from some distance the solar system with a big planet, Jupiter, and the Sun. Jupiter will only reflect 1/1000th of the luminosity of the Sun. So if you look at some distance, it's exactly like we have here. You are completely dominated by the luminosity of the star, and you cannot see the planet. So you need to develop a technique, indirect technique, to detect planets. And one possibility, already mentioned and proposed many years before, but at the time where the instrumentation was not able to give an answer, is if you have the star here, you have the planet here, boom, you cannot see the planet, but you can detect a small wobble of the star, and in fact you can detect a small change of the velocity of the star. So you need to develop an instrument to measure precisely the change of the velocity of stars. And evidently, if a star, let's imagine the Sun, is doing something like this, you have a reason for that. And this is exactly the effect we are looking for. And this picture, so the velocity of a star, it's a relatively bright star. 51 Beck is just at the limit of what we can see by eye. It's a star exactly similar to the Sun. And you see, at some moment, the velocity, this is the velocity, this is the time. At some moment, the velocity, the star is moving in new direction, at some moment receding in the other direction, and so on, periodically with a period of 4.2 days. We do not have any planet in the solar system with a so short period. And if the period is so short, it is a planet extremely close to the star.
We mean that the year for this planet is 2 days long.
Exactly. One of my US colleague, competitors, Jeff Marcy, it's an awful planet because you have to pay your taxes every 4.2 days. So this is okay, we have selected a huge sample of 142 stars similar to the Sun. And we measure we built a new instrument. This was really important. A new spectrograph able to measure small change of velocity. And we start to measure one night, we measure the certain number of stars. After another night, another set of stars, and so on. And 2 months after, we repeat the measurement, and so on. And we add certain amount of measurement. So at no moment you have a moment where you say, oh, we have a planet. No, we have a series of measurements. And after, with a computer, we try to look if we can fit a periodic curve inside. And for some of them it works, some of them not. But the other stars with the changing velocity, we discover it's due to some kind of magnetic activity of the star. So you know that the sun has spots, and the sun is rotating, so sometimes the spots mimic a change of the velocity. Nothing to do with the planet. But one resists to the test, but 4.2 days. Okay, we have been a little bit afraid to add a new wrong discovery, because this domain, searching for planet, was known to be paved by a lot of wrong detection. So we have to be careful. So we postponed the announcement to one additional year, because the star is not visible all the year. So when the star reappeared in the sky, in July 95, we did measurements, and we checked that the period was the same, the amplitude was the same, and the phase of the system was the same. Everything was fine, so we say, oh, okay, we don't see an alternative explanation. We do not know why the period could be so short, okay, but we publish it. And
it must be very close to the sun.
Yeah. It was 8 times the radius of the
sun, of the star.
We have nothing in the solar system like this. And then after, some of our colleagues in US published very soon, I believe they published, it was published a few months after, but with a delay of publication, they have the idea immediately. In fact, the answer was already known before the discovery. In fact, I have to be a little bit technical.
Okay.
You have the star, you have a disk of dust and gas, and at some moment you agglomerate ice particles in the disk. So ice particles has to be very distant, because close to the star you don't have ice particles. But you need to agglomerate ice particles if you want to build a planet like Jupiter. So the theory said that the period could not be smaller than 10 years, because it's a location where you have ice particles. So after, what happened? The mass of the planet will create some waves, some excess of matter in some place of the disk, due to the resonance and things like this. And if this excess of matter will react on the orbit of the planet, and if you do the calculation, not easy, you have an orbit like this, migrating like this. And this phenomena was known from 1980, but nobody take into account in the domain of planets. This was discussed in the frame of galaxies. Let's imagine the Magellanic Cloud, two small galaxies, was trapped in the Milky Way. The Milky Way is much more massive. Let's say the large Magellanic Cloud will suffer the same phenomena and will be engulfed by the Milky Way. This was the goal of this paper. But nevertheless, in the abstract of the paper, it was explicitly written that Jupiter was not born where it is today due to this phenomena. But the planetary astronomer
did not pay attention.
Didn't pay to this. And also you have other reason, because I discussed with the two authors, Scott Tremen and Peter Goldreich. So it was very big name of science. And in fact, it was too efficient. So the time scale for, the time needed for this phenomenon is so short that we should not have any planets. So what is the error? So it was part of the reason why people were doubtful.
All the planets would migrate to
and disappear in the star. And what is original in the paper of 96, just after 51 Peg, was the fact they discovered the phenomena to stop the migration. It's a nice story.
Yeah. So most people are used to Kepler's law and so on, dealing with one star and one planet, ellipsoid trajectories and so on, with no problems of this kind.
Yeah.
But once we have more planets or more mass around the star, all kind of phenomena can happen, and this is what we are talking about now.
Yeah.
I want to remind our viewers that in school we learned that ancient Greeks, Aristotle, and so on, their picture of world was that the Earth is in the center, and stars, sun, and planets are orbiting the Earth. Then we learned that the correct picture is, and it is not correct picture, that the sun is in the middle and everything is orbiting the sun. And if this was true, then this discovery wouldn't be possible. The truth is that both sun and planet are orbiting the center of mass. So not only planet is going around something, also the star is going around something.
Exactly.
And we cannot measure, one would naively expect that if I look at the star, I can see this motion, this projection of this circular motion. That's not true. What we can see is this radial motion going from us and back to us and from us and back to us. How can we see it? Via spectrometry, via Doppler effect, and that's the picture here.
Yeah.
Okay, now after this there was another method, and again, as Michel said at the very beginning, we cannot observe in this way the planet. We are blinded by the star, so only thing we can see is the motion of the star, which must accompany the motion of the planet.
Exactly.
And after this, another very, I would say, ingenious and in some way simple method of how to observe the planet was used, different from this. It's based on eclipse of the star by the planet. Can you comment on that, and can you explain to our viewers and listeners?
The detail is always complicated, but the ideas are so simple. It's a really simple physics.
Yes.
The fact that we have discovered the existence of planet close to stars shows that you have the possibility, time to time, that you will have a transit of the planet between the observer and the star. So what you will not see the planet. The only things you will see is that the luminosity of the star will diminish periodically like this, simply because the planet will cut part of the luminosity emitted by the star. So this, the probability for such a phenomena depends on the distance. And if this hot Jupiter, this planet with short period exists, the probability is something like 4% for 51 peg. So you have to try. Why we do not have any same phenomena for any star? Because the velocity cannot give the inclination of the orbital plane. So it's only if the orbital plane is just in the direction of the telescope that you can observe this phenomena. So you have to, it's a lottery. You discover a planet, you try.
Yes.
If the luminosity is, and nothing happened, okay. You repeat for another object.
If nothing happened, it just means that the geometry was not
yes,
in favor
exactly,
of
simply, exactly.
Yes.
But analyzing the curve of the based on the Doppler effect, you can say if the plane is correct, you can get this phenomena should arrive at such time. And we provide this information for one other planetary system, and to some colleague where we're working together in the States, and with a small telescope, a 10 centimeter telescope in Boulder, in fact, exactly at the good time, they saw a drop of a little bit less than 2% of the luminosity of star. So we can do a small calculation together. The diameter of Jupiter is about 100 times smaller than the size of the Sun. So the surface of Jupiter is about 100 times 100 is it's 10 times, sorry, 10 times smaller than the Sun.
The surface is 100 times.
Exactly. And the the diameter
is 10 times smaller?
10 times, so the surface is 10 minus 4. It's, 10 minus 2.
Minus 2.
10. It's morning. So you can expect a drop of the luminosity by about 1%.
Yeah.
In the case of the first object we observed, it was a little bit more. So this corresponds to a planet a little bit larger than Jupiter. But if you remember your school lesson of mathematics, if you have the mass of a sphere from Doppler effect, you have the size from the transit, you can easily determine the mean density. And the mean density derived by this technique is 0.3 gram per cubic centimeter. So it's less than the density of water. It's 1/3 of the density of the water. So this was a direct proof that we have really a gaseous giant planet. So the last skeptical was finally convinced that we have detected gaseous giant planet. And we can compare to the mean density of Saturn in the solar system, and the mean density of Saturn is 0.7 gram. So it's still more diluted than Saturn. And evidently, this was extremely, exciting observation, very simple but exciting, because after, for example, the Koľko space mission launched by ESA a few years after, and more importantly, Kepler first, and then TESS. So 3 missions reveal a huge number of planetary systems by this technique.
Yeah, so after almost 30 years, we have thousands of planets, 5,000 or something?
More than 5,000.
More than, but not more than 6. Sounds
no, less than 6.
Less than 6.
I don't know exactly.
Okay. Yeah, and okay, a lot of them are gaseous planets. which in some sense we are not that much interested in. What
Yes.
people, at least ordinary laymen, are interested in are rocky planets which are somehow similar to our Earth, and moreover rocky planets in such distance from the star that life can evolve and is stable, the circumstances on that planet. How many, order of magnitude, planets of this type did we observe?
Yeah. Okay, rocky planets are smaller than gaseous giant planets. They are smaller mass and a smaller size. So both techniques have difficulties
To
detect this object. Because the Doppler effect due to the Earth, the impact of the orbit of the Sun corresponds to a change of the velocity of the Sun of only 10 centimeters per second. Let's imagine the Sun is moving so slowly during 1 year. So this just gives an idea of the difficulty.
Okay, can we compare what's the effect of Jupiter on Sun and Earth on Sun?
Yes, Jupiter induces a change of about 10 meters per second.
10 meters per second?
10 meters at the Earth, 10 centimeters per second.
Okay.
So this, you see, the problem. And if you are discussing the second technique, and this is the reason why I was a little bit ambiguous when as a previous discussion. The size of the Earth is 1/100th, the diameter is 1/100th of the size of the Sun. So 100 times 100, the size, the surface of the Earth is 1/10 of 1,000 of the luminosity. So a drop of the luminosity.
10 to the minus 4,
is
yes.
Terribly difficult. Let's imagine you have a star and you have the Earth, an Earth twin going through the disk of the star. This will induce a change of the luminosity of only 10⁻⁴. So it's so small. So you cannot do it from the ground because the perturbation due to the atmosphere kill the possibility. You need to go into space. And this is why Kepler, TESS, and so on, Koľko, was successful, because you are outside the atmosphere, so you don't have the trouble due to the Earth's atmosphere, so they were possible to detect this kind of object. And today we have several planets detected with size smaller than the size of the Earth, but most of them are extremely close to the star. So they are not really Earth twin, because
too hot.
Not necessarily, because if they are close to M dwarfs, so a star with a mass,
it depends on what the star is. Yeah.
And so some of them are in the habitable zone of a small star, but we still not have really good analog of the Earth with rocky planet in the habitable zone.
Okay, one more question to the technical one. For ordinary people, the exciting thing is that we are speaking about planet we are observing indirectly. But from the point of view of astronomer, of the physicist, the exciting part is how to measure things which are almost unmeasurable. And we have mentioned telescopes, we have mentioned spectrometers, we have mentioned spacecraft. What we didn't mention is that if we are going to perform very precise measurement with the apparatus at the normal temperature, then movement of the parts of the apparatus are at the common temperatures are too large, so that they can completely destroy the precision of the measurement. So another part not mentioned yet is cryogenics, the low temperatures of the apparatuses. Am I right? And how is this achieved?
Yes, the Doppler effect. Okay, when we show some slides, huge Doppler effect. It's not the case. In our case, the Doppler shift is so small that in fact you have, this is the original aspect of the technique we have developed. We try to measure the thousands of atomic transitions in the spectra to see the common motion to achieve this extreme precision we need. And as you mentioned, we need to have a very, very stable spectrograph. So the spectrograph is in the vacuum with a thermal control at the level of few millikelvin during the night. So nobody is allowed to enter in the room during several weeks, because after to relax the instrument. And then after you do the measurement, and you need to, what is called calibrate. You need to establish the geometry of the detector. And for that you have to have something stable. So during several years we have been using some lamp, a thorium argon lamp. It's a lamp producing a lot of lines where you can compare to the spectrum and so on. And then after you discover it's not stable enough because they are aging during time. Then after we introduce different kind of optical device, what is a Fabry-Perot instrument, and it's also not stable. And now the most recent spectrograph for this kind of studies use what is called laser comb. It's a special laser producing a lot of lines, controlled with an atomic clock. So you see, it's start to become difficult. And just to have an idea of the difficulty, that for the most recent spectrograph we have, the Doppler shift we are able to measure correspond to a shift on the detector of 1 nanometer. And this is not to be measured during one night, but to be measured during several years, because some planets have a period of several years. So this is technical detail, but okay, the hidden part of the technology is not so easy.
Yeah. But perhaps I was not right. So the problem is to have temperature very precisely determined and not necessary to be very low.
No,
is it so?
The detector, the CCD detector, it's a big CCD, not like you have in your photo apparat, but a little bit better. And you have to keep this detector to minus 120 degrees. So you have some cryogenic, because as the exposure was sometimes longer than maybe half an hour, you need to cool the detector.
Well, but okay, so that's not that deep, that close to helium temperatures. No. It's okay.
But we just put in operation a new spectrograph in Chile, measuring in the infrared. And this is, all the spectrograph is cool at something like minus 100. So, but okay, it's details.
Good. Fine. Back to some exciting things for laymen. As what we were speaking about until now were observations of the star, of the spectrum of the star and of the luminosity of the star. Now, what do we know about the chemistry of the planets, about the chemical compound of the planet? Is it accessible somehow? If yes, how? Because this is important in the future if we want to know, can life be on this planet? The first answer is, are organic compounds present on this planet? If there is an answer to this question, it must be completely different from we were discussing up to now.
Yes. As I've said before, the ratio of the luminosity between the star and the planet is terrific. And the planet we are interested in is smaller planet, rocky planet, so it's still more difficult.
Even more, yeah.
And I would say 20, 30 years ago, the situation looks almost desperate. And suddenly you have a good news coming from nature, because the transit can offer an unexpected possibility. I have to explain this. The size of the Earth, let's say, the radius is 6,000 kilometers, to simplify. In the visible, a rocky surface. But if you look the Earth in the wavelengths of 9.7 micron in the infrared, due to the ozone layer, in fact, all the luminosity in this domain of wavelength will be stopped, let's say, at 6,000 plus 40 kilometers. So the Earth look, in this domain of wavelength, the Earth looks bigger. So if you measure the transit, in the visible, it will be like this, and if I exaggerate, in the ozone, it will be like this. So you can repeat this in many, many different color wavelengths.
Yes.
So it's a natural way to build the opacity of the atmosphere of the planet for free.
Yeah. So if I got it right, we have the light coming from the star.
Yes.
Penetrating the atmosphere, if there is some, around the planet.
Exactly.
And in this atmosphere, some of the lines are absorbed by the chemicals present in that atmosphere. So from the spectrum coming to us, we have fantastic information about chemical compound of that atmosphere.
You don't need to build an instrument. It's made for free. But the cost of this is the effect is extremely small.
It's tiny, yeah.
It's also, you have the big luminosity when the planet is behind, and you have the big luminosity when the planet is in front, and the difference between two, it's a small
and
effect.
It's not the effect of the whole planet, only
Exactly.
a small ring of the atmosphere.
Exactly.
Okay, so, and that this is visible is due to, I would say, enormous development in the technology. Is that right?
And size of telescopes.
The size of telescope during the last 30 years.
Because you cannot have long exposure, but you have to do the measurement just during the transit.
Which can be a couple of days for some planets.
Let's say typically it's a few hours. So you see, so you cannot integrate long system. Okay, you can wait the second one and add several, but it starts to be a long measurement. But if you have a huge telescope, you collect enough photons to see the difference between the two spectrum, behind and in front. So it's one of the reasons, no, it's not the only one, but it's one aspect of the building big telescope. Like presently Europe is developing a telescope with a primary mirror of 39 meters. Let's imagine the size of the telescope. The mirror is 39 meters. When I did my studies, long time ago, the record was the famous Palomar telescope with a diameter of 5 meters. And the size presently is 39 meters. And it will be put in operation in 2028. So not so
far from
it's already in development, it's constructed. And the other one is a James Webb telescope, smaller one, it's only 6.5 meters, but in space. So evidently, the James Webb telescope will devote quite a lot of time to do this kind of measurements. Mm-hmm. Because maybe I can explain that.
Yeah, please.
So this technique gives access to the spectrum of the atmosphere of the planet and of the star. So what we dream to okay, we can do some physics. If it's hazy, temperature, and so on and so on. And for example, recently, the James Webb telescope...
The temperature we know again from Doppler, or...?
No, only for this technique.
Okay.
So, and you detect, for example, that you have some molecules in...
Okay.
For example, the carbon dioxide was detected recently, and many other molecules, and so on. These have been detected already. But what we dream to detect, it's what is called biomarker. So let's say it will be oxygen, because on the Earth, oxygen is part of the life. Nitrogen oxide, methane, water, and so on. So at some point is a problem of biologists and chemists. What are the elements having a significant, to be a significant proof that life is acting? Okay, it's not easy answer because you postulate something on what kind of life, how it works, and so on. So this is probably the only possibility at short term to have to detect some hints that maybe life is acting here. And
this is, well, the whole method is based on a assumption which is very natural but cannot be taken as guaranteed unless proven to be, that the physics is the same all over the universe.
Yes, I'm convinced of that.
Yeah, and that this method did function is the proof. I would say that it cannot be that the Doppler effect is different here and there, and we have these results. It cannot be that the spectra are the same, meaning that at least the atomic physics is the same here and in the stars. And here we are pushing this principle, for which we have already proofs in this domain, that even life and even organic chemistry is going to function in the same way there as here. In that case, we can know from the terrestrial biology what are the important molecules and to look for them in those planets.
But evidently we do not absolutely prove that life could not work a little bit differently.
Of course.
But I will advocate nevertheless on our own life. We have some constraints. We cannot do anything we want. We are looking for rocky planet with water, liquid water. So first, water is an absolutely fascinating solvent, helping for chemistry. So this is first aspect of this. But one of the most significant, important aspects, that, okay, our chemistry is based on the carbon, because the carbon is the only chemical element having been able to produce extremely complex molecules. And this is absolutely critical, because for me, the most significant characteristic of life is the capability to transfer information from one generation to another one.
Okay, we are speaking DNA now.
DNA, and okay, some people have dreamed to find another way, but up to now, it's the only way to transfer the information.
The other way based on carbon or based on silicon?
No.
Based
silicon,
on carbon?
The largest molecule of silicon is too small.
So that's the possibility that the passing on information could be somehow that in principle there can be some other chemistry except of the chemistry of DNA, which could provide the passing on information, but we don't know.
No, we don't know. And probably we don't have any hints that other molecule could do, as a chemical element could help be in replacement of the carbon. So one is the consequence of this. If you have a temperature higher than 120 degrees approximately, the long chain of atoms of the DNA will be broken. And you cannot transfer life. And it's what you do, all of you, when you are eating aliments. To prevent the degradation by bacteria, you simply eat above 100 something degree. And life is killed, is stopped. And the other way is to put the aliments in the fridge at minus 20 something in the freezer, because the chemistry is so slow. It's one way to stop also. So when we astronomers are looking for rocky planet with water, it's a solvent. But in addition, is a domain of temperature where you can have long chain of atoms and able to transfer the information.
So that's the temperature interval.
Yes, exactly. So it's not a anthropogenic idea. It's simply a byproduct of the physics.
Yeah.
If we are searching life for it.
Okay, so at the present, we can, in principle, and not only in principle, we can do this kind of measurements, but still we are several years from the very big telescope, which will improve things. What's your estimate of if there exists terrestrial-like planet outside somewhere? What are our chances? Well, what we do about the solar systems, we already know 5,000 and more planets. What we do about varieties of solar systems, and what we can deduce of how probably the Earth twin is somewhere out and we are going to find it.
Yes, okay. First we have to find a large enough sample of Earth twin.
Yes.
And
rocky.
Not too far away to have enough photons coming from this.
Yeah, so that we can see.
Yeah, we can see. And then after you have to develop the instrumentation to try to find this kind of specific molecules, typical of life development. And this maybe it could be made in few years. It's not because the 39 meter and with a very evolved spectrograph to be Andes will be developed. This is a few years, I don't know. And then after you develop, you observe first one, nothing. You observe a second one, nothing, and so on. It's not a proof.
Yes.
You need, and after a certain amount of time, when you have, I don't know how many, but you have tried 100 Earth twin and you do with the good temperature and everything fine,
yes.
And you don't find any trace of the good molecules.
Yes.
We
start to be suspicious.
Feel to be alone.
Yeah.
But okay, I cannot anticipate how long we need to do it. But it's a nice question, because what could be the answer? The answer will be, we are not alone. And when I say we, it's life. It's
not mankind, but
no,
life.
It's not something similar to
Absolutely.
Bacteria or unicellular form organism in the atmosphere or in the ocean of a distant planet is life.
Yes.
So this will fulfill the answer of old philosophical question. Do we have other world in the universe with living species?
Yes.
After, it will be difficult to go further. Okay, we can improve the chemical determination and so on, but it's difficult. But we will answer this philosophical question.
And this can be done within decades.
Yes, I hope so, but it's not a proof.
Yeah, if it is, well, if if the chemistry is found there, then we can say that very probably the circumstances there are in favor of life, something like that.
But I believe we can have as a dream. In the solar system, during the last decades, we have discovered absolutely incredible new things. Okay, people was looking if in the past maybe life have a chance to be developed on Mars, because we know that a few billion years ago liquid water was flowing on the surface of Mars.
We are now speaking about possible life within our solar system?
Yes, or past solar system.
Yeah.
So it's because if at some, no, not if, we know that at some moment liquid water exists and atmosphere, because it exists on Mars 3 billion years ago. Maybe life chose this opportunity to do something. And today we cannot dream to find beautiful fossils. No. But just small chemical alteration of rocks. This kind of small change of the chemistry of rocks could not result from normal physical process, but from life development. Isotope ratio, things like this. So this is the reason why year after year you have space missions sent to Mars to try to analyze things. And they found already first geological evidence, some kind of rocks produced when you have liquid water, and so on and so on. But I will try to go a step further. On the Earth, we know that life, living life, exists very deep in some faults, rocks, break of mountain rocks, 3,000 meters. Yeah. You have bacteria. So what we know on Mars, that we had in the past liquid water, we had volcano, so we know that we have temperature down inside Mars. And so we can anticipate that we are almost sure in the deep rock of Mars we have liquid water at nice temperature for many, many billion years. So you can dream, maybe you still have living, and this is not a fantasy of my side. It's at the present time, all the space agency discussing what is called sample return. Rocks taken on Mars and sent back to the Earth to do analysis are really considering the danger to do this experiment and to bring new kind of living species on the Earth. It's not a fantasy. You can, okay, it's not at the surface. Evidently at the surface, the gamma.
It was in the depth and coming.
Yes, for some
geology.
Yes. So we cannot refuse the possibility that maybe in the deep rocks of Mars we still have some living form of elementary form of life, evidently. And this is one possibility, but the catalogue is not limited to this. Several decades, a space mission, a US space mission, did some beautiful pictures of the surface of different satellites of the solar system. Big satellites around Jupiter, big satellites around Saturn. And one of them, Europa, is covered by ice shield, not a glacier, but an ice shield. So you have liquid water below, and you have crust of ice, but due to the tidal interaction between the different satellites, the form of Europa is obliged to slightly adjust to the potential of Jupiter.
And to crack.
and crack. And so when you have a crack, some water go up in the floor. So you don't need to dig to take a sample of water, because naturally the water will arrive.
Ooh, and it froze, and it freezes
But it froze immediately. But what you can do is to send a spacecraft, pick 1 cubic meter of ice, melt it with, let's say, a passive nuclear device, and then after you filter, and if you are lucky enough, you will find some unicellular form of life. And what you can do is to analyze if the DNA is the same as of the terrestrial one. If the recipe for life is universal or not. Because it's true as it's not a transfer of life from on these two systems.
Because there's no way.
No way to do it. No.
Yeah.
So it will, it will go much further than just detect. Okay, the philosophical question rely on exoplanet, but this is something more. It's a universal aspect of the chemistry of life, because we do not. The DNA is a replicating molecules, but we do not have proof that we can. It's the only form to do it. So, okay, this is for long-term future. It's not for tomorrow, but we still have some, expectation to go much further in this kind of question in the coming, I don't know, 20, 40 years, I don't know. And it's not finished. The same spacecraft observe Encelad. Enceladus is
another moon of
Saturn. So it's still further in the solar system. But what was discovered, that some moment you have a geyser, huge geyser, with a jet of the water going up to 100 kilometers and more. And it is already known it's salty water. So you have also water underground, and probably temperature not bad because it's a liquid water. And so you already have some space mission with the goal to go through this ejection of water.
Okay, so
do some analysis.
There's no need to go down to the moon. You can
and to analyze if you are lucky
yes.
to see if this something is interesting. You see, it's few dozen years ago, this was completely unexpected. When I was a student, nobody claimed that we can have still living form of life in the solar system except the Earth. And no, the problem is more complicated.
Okay, so we started with the distant solar systems and trying to find the planets there, then trying to see if the circumstances on the planet, some of them are in favor of life, and then in this discussion we came back to our solar system, speaking about things at least as exciting.
Oh, yes, yeah.
Okay, so I would say that it's not sure if the life is present also in other parts of our solar system or if in other parts of the universe, but definitely when the life is present at the level that the science is present, it's pretty much exciting.
Yes, yes. And following this kind of suggestion, it will be extremely sad if we left science to the next generation with no big questions. And for children today, it's good to have this huge question facing them. Okay, I'm sure that I will not see the results of all this experiment, but you have dark matter.
Yes.
Missing a huge amount of matter we are sure this matter exists in the universe, but we don't know what it is. For what is the reason for the accelerated expansion of the universe? Do we have life with the same recipe that we have, and so on? We have a huge black hole discovered on the very remote galaxies from very soon after the beginning of the Big Bang.
Yeah, so
what are the mechanisms to form this black hole?
They should not be there. That's not just
so this is not a small question. This is a huge question, and this is only for astrophysics, and you have several answers. But you have the brain functioning, so it's good. So if I would be myself a child today, I will really consider to do science again. But I don't know in what domain.
Yeah.
It could be a different domain, but you still have nice questions.
Fine. So we are almost out of time. The last thing I would like to mention is that probably we do not have you for the last time here in Slovakia, because the next year the Starmust Festival is going to take place here in Slovakia. I would like to ask you if you can say few words about the festival.
Yes. Starmust is incredible kind of festival. It's a mix of science, high-level science, but not for specialists, for the general public. And this is explained during several lectures by prominent people of quite different fields. Astronomy, astronautic, biology, and oceanography, and other things, but in an easy way to be followed. And cherry on the cake, you have music after. So every day you have science and music. And this festival is the 7th one. It will be here in Bratislava. And I was myself involved in the 4 of them. And it's absolutely exceptional. The last one was in Yerevan, in Armenia. And every afternoon, you have between 6,000 and 8,000 people. Attending. And if you have seen the movie shown 2 or 3 days ago, it's incredible. The quality of the music was absolutely fantastic. As this festival was coming from the idea of 2 people. One is Garik Israelian, is an astrophysicist working in Canary Island in Spain, and the other one is Brian May
from Queen.
So
who is astrophysicist?
He's also astrophysicist, and so this mixture, and Brian May can ask a lot of people, and they will come. And Garik can do the same. And for example, in Yerevan, I don't know, it's something like 50 lecturers were there, something like 12 Nobel Prize. So you have quite, myself, I love to go for different reasons, but one reason was to listen what happened in different fields of my own one, because always you can learn a lot. And the second point, this is common to all the speakers, you have, I would say, the commitment to go in different university, high school, public, to give public lecture. And for example, in Armenia, I don't remember, maybe 60 different lectures were given in the full country. And I'm sure that here it will be the same. And eventually you have to adapt the discourse to where you are going to. So this is, and always music. For example, when I was in Yerevan, my plane was leaving at 4 in the morning or something like this, terrible schedule. So I left the center of Yerevan at midnight, and still at this moment you have a group of music on the place facing the opera, with groups and so on, thousands of people and so on. So this is the magic of this festival. I believe it's unique to have this size and spirit.
Okay, so we very probably will have Michel here in Bratislava also next year, and all of you are invited to this festival, which seemed to be quite interesting one. Michel, thank you very much.
Thank you so much for the invitation.
Okay, we did it.
It's nice to have supported. It's a nice story.
Yeah.
Yes, it's
absolutely.
Yes, and evidently we are limited in time, but you have so additional ideas. So keep alert that probably in the coming few weeks, months, I don't know, they will publish several astrometric orbits. So not the velocity, change of the velocity, but change of the position, because the satellite space mission called Gaia and measure exquisite position of stars.
Is the European? Or
yes, European, and they have discovered quite a lot of
so they are now measuring.
Yes, they have the precision needed to
the perpendicular direction.
Yes, and for example, this is thing, and yes, I believe maybe I have to say this to Garrick, to invite somebody from this
to give a speech about that.
Yeah. Mm-hmm. It's an additional technique.
Yes.
So it's not.
And what's the principle? What's the principle of the additional technique?
Gaia, it's an interferometer.
So
interferometer.
It's still.
Yes.
Still
an interferometer, but a baseline of few meters, with a different technical tool to arrive at this height. It's terrific. The precision is so huge. You can dream for that. For example, the typical individual precision of the position is 50 micro arc second. So just okay, we cannot say what it is. It's a small angle, but 1 milli-arc second is the angle coming from 2 lamps on the moon with a separation of 1 meter. It's a milli. So 50 micro is 20 times smaller. It's 2 lamps on the moon at 5 centimeters. Okay, and this is made for billions of stars. So you see.
So this is going on now.
Yes, yes. And they have a huge amount of byproduct. For example, you measure the position, and you have a star. You can see the wobble, something at position, and so you see it's a binary stars, and you determine by the Kepler law the mass of the companion.
Yes.
But you cannot see it, and you detect it's maybe 10 times the mass of the sun, and it should be visible. And what is the consequence? It's a black hole. So they are right now discovering quite a lot of black holes only by the astrometric technique, and so on and so on. It's nice. Yes. And yes, I have to because I've been working with Garrick in exoplanet domain, so I can ask him if he considers
to invite someone from this field. Yeah.
Yes, yes.
Yeah, do it, please.
And it, in some sense, is domain relatively easy to explain.
Yeah, that's right.
It's right. Because some domain of science are absolutely exciting, but maybe more difficult to explain what for example, the
especially theoretical ones.
No, okay. It's awful. No, but I did many years of theory, so I'm allowed to say this. Yeah. But you see, for example, the Nobel Prize in Physics this year, because they have been able to develop laser pulses. Social, I don't know what is the name. I don't know. Is it new terminology for the Terra? I don't know what is. so small, so they can do images.
Atto.
Exactly. And they measure the position of electrons at some moment of it, an atom. Yeah, and a few years ago, Gerhard Mourou and one of her students, I don't remember the name of the student, she will be at Starmus, develop a high intensity laser.
Yeah, that was the similar.
But with a short impulse, and so they are able to push atom. And so I was with Gerhard Mourou recently, and during a lecture, and somebody in the public asked the question, can we use this huge intensity laser to destroy a satellite? I say no, because the energy is 1 watt. It's a very small energy, but during so small time that the intensity is terrific.
Yeah, the force is big because
the
impulse is the same.
But you push only an atom. You don't push a satellite.
Yes.
And so you see, it's nice. Huh?
It is.
Okay, thank you so much for the invitation.
Yeah,
and see you in May.
Diskusie pod lampou existujú iba vďaka vašej podpore. Ak považujete program pod lampou za zmysluplný, pomôže nám už 1 euro za diskusiu. Vopred vám veľmi ďakujeme.